Hey students, so now we're going to talk about video 14b, which is the physical joining processes, so adhesives and welding. And so let's get right in it and look at some of the differences here. So when we're talking about adhesives, one of the big challenges is that we often have to allow time for curing. And so the fixture has to be able to grab something and hold it for an amount of time. But that also means that the fixture often has to be low enough cost that we can build multiple fixtures. It typically does not work to be able to build one fixture, take it out of production for 3 hours while something cures, and then, or overnight if it's an oven cure, and then bring it back and put one more part in. So that often sets a cost threshold. We have to have materials on it so that if we do get adhesive overflow onto those materials, it's easy to get the adhesive off. So often has to be plastics or something like that that are really unsticky to the adhesives. If we have something that has a two-part adhesive, it means that we have a fairly short cure time often, and so we have to be able to have space between the parts so we can put the adhesive on and then get the parts put together. Also, we often have to clamp along the entire join, and so wherever the join is between the two, it's not like one where we can just hold it in place. We often have to clamp and apply pressure once we have the adhesive on there. Very often also adhesives really make that joint be slippery, so it's hard to hold those two pieces in place because they now have this adhesive which acts as a lubricant in them. So the main ways of activating adhesives are by heat, moisture, hot cooling like a hot melt glue, and then pressure. And so you can ask the question, how would each of these adhesive activation attributes change the fixture? So you can think of, if we had to add heat or it had to be in a moisture environment, what if it had to be something where as soon as it cools, the adhesive will be done, and maybe it will create a lot of heat, or maybe I need to not let the heat out of it for as long as I can. And then if I have to use a lot of pressure, so think about what those would change. When we think about welding fixtures, we're actually going to spend longer on welding fixtures because that's going to be one of your projects. And so we're going to talk about welding fixtures today, and then we're also going to talk about them later and have a perspective from industry from someone who works at Woodstone, there we go, and makes pizza ovens and makes the fixtures for them. So what specific concerns do you think would apply to a welding fixture? If you start thinking about them, the heat transfer and thermal expansion is one of the biggest. We're dealing with a ton of heat when we're doing welding, and so we may have to keep that heat in the weld, or we may have to get it out of the weld, but we're going to have to deal with it, and we'll look at that a little bit. Thermal expansion is huge. When you heat that edge, it's going to get longer. If we've clamped it at both ends really, really hard, then it's going to bow out to the side, and that's not going to be what we want. And so often on those fixtures, you have to clamp them at one end and have the other end so it clamps and holds the parts together well, but those clamps are free to slide somehow. We don't want to impart any distortion to what we're doing, and we need to have the location be correct after the lengthening happens. We probably can't over-constrain here. Over-constraint gets to be much worse because we're already dealing with this thermal expansion, and so if we have already over-constrained the part and then throw in a big force agent like expansion, that will really cause a lot of troubles for us. So just to remind you, the way to determine thermal expansion is that the change in length, delta L, is equal to the coefficient of thermal expansion, alpha, times the original length times the change in temperature. So remember, the units of alpha, the coefficient of thermal expansion, are often in meters per meter degree Celsius or inches per inch degree Celsius. Sometimes they're in inches times 10 to the minus 6 per inch degree Celsius. This is just to make the numbers work out better. And so here you can see aluminum has a really big coefficient of thermal expansion, and glass or Pyrex have really small coefficients of thermal expansion. Here on the light blue column, well, they're both light blue. Anyway, one of them is metric, one of them is US customary units. Oh, I'm standing in front of a bunch of units. Sorry about that. Okay. So when we think about welding, some other things that we need to know is what process is going to be used. So there are many different welding processes, and there are two things we need to think about. One is that three things. One is that the amount of heat input is going to be very different depending on whether we're doing laser welding or gas tungsten arc welding. And so knowing the process that you're using will give you an idea of whether you're dealing with a bunch of heat input or a small amount of heat input. Also, considering the materials that you're using, you can find out how prone they are to distortion as well as the thermal expansion. And then finally, with this, which is not on this slide, is thinking about the size of the different pieces of equipment. So what it takes to get a laser to a location can be very different than what it takes for TIG welding versus MIG welding versus stick, and or gas welding. So all of the processes require a different size access and will produce different amounts of heat, and then you have to deal with it in the parts that are there. So this is a bumper that I would like to have. If anybody wants to make a fixture and weld me one for my Jeep, that would be great. Thanks. So we need to locate the parts correctly. We have to clamp them while they're loose into the right location. We have to have ways for the welding atmosphere to get out, so we can't have it closed up and building up gas inside of it. We need to be able to vent that both for operator safety and also for the weld to work well. We need whatever the welder to be able to access it, and we may have to get heat out or keep heat in, as I said. So either insulators to keep heat in or conductors to get heat out, and then have to have a grounding path because it requires a full circuit, and so there has to be a grounding path out of the fixture. That's often not that hard a requirement. Okay. So what do you think is the hardest of these to plan? I would say that it is either locating the parts or clamping the parts to deal with distortion is by far the hardest thing to plan for. So we said that we might have to keep heat in or we might have to get heat out. And so if we're doing gas welding, we can't have the heat leave too quickly or the weld will actually crack. And so in that case, when we're doing the welding, we may have a plate underneath part of our fixture and put a ceramic bar in that to keep the heat from flowing out very quickly. Conversely, if we're doing arc welding, we'll end up with too much heat, and we need to dump that heat out of there to try to prevent it from warping things. And so very often we will put a conductive bar in that place. You can also, to keep heat in, you can minimize the conduction area and leave an air gap behind it. So this fixture over on the right would do the minimal amount of heat removal. The heat conduction is Ka delta T, where A is the area of contact between the two. And so the more area you have in contact, the faster the material will, or the heat will conduct out of it. The K is the heat conductivity, and so that's why you might use something like ceramic that has a very low heat conductivity so it doesn't pull it out. If you're trying to get the heat out for arc welding, then you would use copper or bronze or something like that that pulls it out quickly. So you can see right here, this is a fixture, holds the part in place using a it's got a little tube on the back of it like it might be pneumatic, which would be a little odd, but anyway, you can see that it's got this copper bar underneath. With resistance welding, we have to be careful about magnetic materials, and so we may have to insulate parts of the fixture for that. Strategies for welding overall. We often want to use gravity when possible. Magnets are a really good way to do welding, though you have to be careful because those magnets will tend to attract grit and dust and particles over time, and so they become a less and less good way to fixture something. So it's often good to have a locating pad and then have the magnet be the clamp rather than the clamp and the locating pad, if you can. Having hold down plates is often a good way to do things. That way, instead of contacting in one area, you're contacting over a distributed area, and that both helps to keep the part from warping but also reduces the pressure in any one location, so it allows the piece to slide more easily because it doesn't have as high a normal force at any one place. There is a link down there to get to a robotic welding video that's interesting to look at. One quick item from this, there's a video that you can watch all about the design of this fixture. It is not a very fast moving video, but one of the things that they talk about there is that in welding it often makes a lot of sense, rather than spending a bunch of money on a fixture to have precision, to make your parts undersize and then use things called shim packs to put them in the right place. And so what they do is these little blocks, they make all these little blocks undersized, and then they have layers of thin pieces of metal that have the holes drilled in them so they won't run away when you bolt this down. But you can put fewer or more of those little thin plates of metal under there to tune exactly the place that you want the fixture to be. That's a really good way to do a fixture like this. Typically a welding fixture doesn't require huge amounts of precision, so this is a way to create it with even lower precision and then to gain that precision in just through adjusting it as you build it the first time. Some ideas for welding. One idea is to use these lift-off fixtures. So you can use this. You can see how this entire thing would be put down. It has some guides to hold it in place and a locking arm right here. It also has handles to make it easy to put in, and then it has these big areas where the welding is going to happen. Maybe it happens around the edges, maybe it happens in these windows, but it has the access, but at the same time it really just clamps the entire part, has a bunch of lightning holes drilled in it so that it will be lighter and easier to deal with. And you can see that this company uses a ton of them, and they have them worked out so that they can stack on this table somewhat effectively. Now the handles that they have make them install very quickly but make them not stack very well. Anyway, so they have some cutouts to be able to do that. Just a way of dealing with welding fixtures that are kind of big and bulky. All right, and then one last thought for welding fixtures especially is that you will often have to put in weld spatter deflectors. And so spatter comes out, if you remember from 231 when you were welding, there was stuff flying all over the place, and that will stick to metal and is hard work to get it off. And it will, on your fixture, it will melt through vacuum tubing and air lines. It will stick to things and cause pistons to not operate anymore. It can start fires anywhere that there's a hydraulic fluid. And so one of the big things for a weld fixture is to try to cover up the things that are really important so that they will not be damaged by the heat. All right, we're going to talk about this in class, and then we're also going to work on it more when we talk about welding in industry, and you're going to get a lot of chance to practice this on your project. So I will see you in class. Thanks.